Hey, here we go. This is the blah blah. Hey, here we go. Here are the last two subtasks, 5 and 6. You can find those on pages 5 and 6 of the homework. So the idea here is that we actually can use certain values that we know about an ecosystem's energy to predict other aspects of the ecosystem. I'm going to bring this back to the idea of gross production. We talked about gross production, or GP, as the total amount of organic matter in an ecosystem. This was brought up when we were talking about succession, and we noted that as succession proceeds, whether it's primary or secondary, the gross production, or the total amount of organic matter in that ecosystem, should continue to rise. Now that is a very valuable number, but it does take into account all of the organic matter, including ATP and cellular respiration processes that are eventually going to be lost from that ecosystem in the form of heat or other chemical transfers of energy. So it actually might be a good idea to remove the amount of energy that we will lose due to respiration and heat and think of this new number as the net production, or the total amount of organic matter that you have if you sort of discount and erase cellular respiration. So, net production is going to equal gross production minus respiration. You can also flip this equation around a little bit to determine any of the other values. As long as you have two of them, you should be able to find the third. Now, the challenge for you in the learning targets is going to be to use the information right here to construct an energy pyramid. Now again, I want that energy pyramid to be proportional, so the width of those pyramid blocks should be proportional to the amount of energy in them. They are probably going to decrease by about 1/10 of the size every single time. The other thing that I want you to make sure you do is that you label those blocks with the trophic level, and you include the amount of energy as a number and a unit that they contain. So here's the information. The solar energy received by the grassland is going to be 5 times 10 to the 5th kilojoules per meter squared year. So that's the value. The net production of the grassland is 5 times 10 squared, or 500, kilojoules per meter squared year, and its gross production is 6 times 10 squared, or 600, kilojoules per meter squared year. The total energy that is passed on to primary consumers is 60 kilojoules per meter squared year, and only 10% of this energy will be passed on to the secondary consumers, at which point this pyramid will end, as there's not going to be enough energy to viably create another trophic level on top of the secondary consumers. So I'll show you the answer for that one in the next video, but I want you to take a shot at constructing that pyramid according to those instructions. I'm also hoping that you could calculate the energy lost by the plants due to cell respiration itself. If you need to, you should be able to rearrange that equation to solve for R. Now, we've talked about how energy flows and nutrients cycle, and so we're going to review that here for just a moment. The sun is the initial energy source for all ecosystems. That energy is going to be sequestered and grabbed by producers, autotrophs. They can use that energy to make organic molecules. None of these other organisms can do that, which is why they're going to start every single food chain. Now, if we're looking at just the red arrows, we're going to be tracking the energy. And some energy is going to be lost as heat to respiration. Some of that energy goes on to consumers. They are going to lose heat to respiration, and some of their energy will go to decomposers. Same thing with producers, as those decomposers take those organic molecules and use them to build themselves. Now, decomposers will lose heat due to respiration as well, and that is where our energy flow stops. It is one directional, from the sun through the food chain and leaving those groups as heat. Nutrients work in a fundamentally different way. Nutrients do not come from the sun, but rather cycle around and around, beginning at our inorganic nutrient pool, where plants can uptake those inorganic nutrients to produce organic nutrients, like sugar. Those nutrients then pass to consumers. Consumers will then pass those nutrients to decomposers if they die. Same thing with producers. And the decomposers and saprotrophic bacteria, decomposers, will put those nutrients back into the inorganic nutrient pool. So there's a summary of these steps right here. I'll just read them for you. Nutrients cycle within an ecosystem as nutrients are recycled. Nutrients from weathering of rocks can enter the ecosystem. That harkens back to the phosphorus cycle. Nutrients recycled from decomposition of dead organisms. Nutrients move through the food chain by digestion of other organisms. Nutrients are absorbed by producers, plants, and roots from the inorganic nutrient pool. And of course, nutrients can be lost by leaching or sedimentation. In other words, they can return back to rock in the earth. Energy flow. Energy enters from sunlight. Autotrophs capture that sunlight energy. Energy flows through the trophic levels or stages of a food chain. Energy transfer is approximately only 10% from one level to the next. Energy loss is due to material not being consumed, not being assimilated, not being ingested, or being excreted. Energy passes to decomposers or detritivores or saprotrophs in dead organic matter, and eventually at all levels here, heat energy is lost due to cell respiration. So with that review in mind, there are a couple of tasks I'm hoping that you can complete based on this diagram right here that again shows the movement of energy and has values and the units of energy that we are using, which are kilojoules per meter squared year. There are a few empty boxes here, and I'm hoping that you can again use this equation to calculate the net production of the autotrophs and compare the percentage of energy lost by respiration in autotrophs and heterotrophs. I would also hope that you can suggest a reason why there is going to be a drastically different amount of energy lost to respiration between those two different groups. It is not the same, it's very different, so why would one group lose more energy to respiration than the other? With that, the next video is going to show you the answers to all of those tasks, but do please attempt them before you look at the answers.